Assalamu alaikum students. I hope you're all safe and sound. Welcome to the 8th lecture on analog and digital iconic circuits, in which we'll study maximum symmetric swing for uh, different BJT amplifier configurations. So this is a familiar diagram. We have already analyzed this figure in one of our previous lectures. It is a plot of the output collective to emitter voltage of a BJT uh, versus input based to emitter voltage of the device, and is called voltage transfer characteristics of BJT. So this this region marked within the region of the curve marked within the dotted lines represents the operation of the transistor in the active mode, and this is the mode in which transistor acts as an amplifier, because for small changes in VBE we get large changes in VCE. So as can be seen that as VBE decreases, VCE increases, which drives the transistor up the curve towards the cutoff mode. And as soon as it enters the cutoff mode, um, it turns off and there is no more amplification. So the positive swing of the amplifier or the transistor, which is given by the positive swing of the output voltage, it is limited by the operation of the device in the active mode. So as soon as it leaves the active mode and enters the cutoff mode, um, we, the output voltage does not uh, swing any further. Similarly, uh, as VBE is increased, VCE decreases. The output voltage of the transistor, it decreases, which drives the transistor towards the saturation mode. So the negative swing of the amplifier, which is identified by the negative swing of the output voltage of the amplifier, it is limited by, again, the operation of the device within the active region. So as soon as the device leaves the active region and enters the saturation mode, um, the negative swing of the output voltage, the output voltage in the negative direction does not swing any further. So the swing of the output voltage for a BJT amplifier uh, is limited by the um, on the positive side by the cutoff mode and on the negative side by the saturation mode. So we define the maximum symmetric swing of a BJT amplifier as twice the minimum value of the magnitude of uh, positive swing and the negative swing. So we compute the maximum positive swing, we compute the maximum negative swing, we identify the minimum of the two in magnitude, and then we multiply that with 2 to get the maximum symmetric swing of the amplifier. So in order to find the maximum symmetric swing for different BJT configurations, we will compute the maximum positive as well as maximum negative swings of the amplifier, because once we have those numbers um, or expressions, we can easily find the maximum symmetric swing of the amplifier through this definition. So we start with the common emitter amplifier configuration without the bypass capacitor, in which I have labeled. So this is the same circuit as we have analyzed before. I've labeled the so since the output voltage is taken from the collector, so I've labeled the output voltage as VC. So this is the total voltage. Remember the notation we use. So it's small v and capital subscript C. So this is the total collector voltage. It is the sum of DC plus AC voltages. Whereas the load voltage is just the AC voltage. So it is small v and small L. So it is just the AC voltage, because the DC component of the output collector voltage is blocked by the capacitor. So across the load, we just have the AC voltage, and then this is the total collector current, DC plus AC flowing into the collector terminal. And here at the emitter, I have labeled the total emitter voltage by V subscript capital E. So like I said, the total voltage across the load is just the AC component of the collector voltage, which I represent with V subscript small l. And uh, we notice that during the positive half cycle of VL, so as VL swings in the positive direction, collector current decreases uh, because this voltage VCC minus total the collector voltage. This is the voltage across RC. So so as VL increases, AC component of V total VC increases, and since the other end of RC is connected to VCC, which is fixed, this voltage is increasing. So the voltage across RC decreases, which decreases the current through RC. So as VL swings in the positive direction, current through RC is decreasing, and current through RL increases obviously because VL is increasing in the positive direction. So the load current increases, current through RC decreases. So this decreases the collector current because collector current is the current through RC minus the load current. So load current is increasing, this current is decreasing, so collector current decreases. So the maximum value of, or the maximum peak value of VL in the positive direction is observed when IC, because IC is decreasing, the transistor is moving towards cutoff. So maximum positive peak for VL is observed when IC becomes 0. So VL will reach its maximum positive peak when the transistor enters the cutoff mode. That is when IC becomes 0. When IC becomes 0, this is this current, this expression, which is the current through RC, it becomes equal to the current through the load. So when IC becomes 0, current through RC becomes equal to the current through the load. So under this condition, I have represented, because under this condition, we observed maximum positive peak of VL. So I have represented VL, I have denoted VL with VL maximum positive. So this is the output load voltage when the transistor enters the cutoff mode. And this represents the maximum positive peak of the output voltage. So we solve this equation by realizing that this total VC is the sum of DC component and the AC component. Since the AC component is equal to the load voltage, and under this condition, we have represented load voltage by this notation. So total VC is capital VC plus VL maximum positive. So I take VL maximum positive on the other side. It is this term. And I realize that this left-hand side, this VCC minus capital VC is the DC voltage across RC. So VCC minus DC component of collector voltage is the DC voltage across RC. And if we divide that voltage with RC, we get IC, the DC current, this DC component of the collector current. So this thing is equal to IC. So setting this thing equal to IC, solving and realizing that 1 over RL plus 1 over RC inverse is equal to the parallel combination of RC and RL, we get this expression for the maximum positive peak value of the output AC component of the output load voltage, which is the load voltage. So the positive swing of the load voltage or the output voltage is given by this expression. So it is set by the DC component of the collector and these two resistors. Similarly, we observe that as VL swings in the negative direction, the collector to emitter voltage decreases. Why? Because the current through, first of all, the current as VL swings in the negative direction, current through the load resistor switches its direction because VL is negative now. So it moves up from the ground up the RL into the collector terminal with increasing magnitude. As VL increases in the negative direction, this opposite current increases in its magnitude. And secondly, as VL is decreasing, as VL is increasing in the negative direction, the AC component of collector voltage is increasing in the negative direction, which decreases the total collector voltage. And in turn, that decreases the voltage drop across RC, increasing the current through RC. So because of this, the collector current increases, which increases the emitter current, which in turn increases the total voltage at the emitter. So total voltage at the collector is decreasing, total voltage at the emitter is increasing, so VCE decreases. So let me go back to the circuit. So what I just said is that as VL increases in the negative direction, IL, because VL is negative, IL flows upwards now with increasing magnitude as VL increases in the negative direction. So IL flows into the collector in the upward direction with increasing magnitude, the AC component of IL. Uh, and since VL is increasing in the negative direction, the AC component of total collector voltage is increasing in the negative direction, which when added to the DC voltage decreases the total voltage at the collector. So this voltage is decreasing as VL swings in the negative direction. Hence, the voltage drop across RC, it increases because this voltage is decreasing. This is a constant voltage. So the drop across RC increases, which increases the collector current. I'm sorry, which increases the current through RC. So current through RC is increasing and the load current flowing into the collector is increasing, the AC component. So this increases the total collector current, which increases the total emitter current because IC is equal to alpha IE. So IE increases, which increases the voltage VE. So VE is increasing, VC is decreasing, VCE decreases. So as VCE decreases, the device is driven towards saturation, and we observe, so the device moves towards saturation, and we observe that VL reaches its maximum negative peak when the transistor enters saturation mode, because beyond that point there is no amplification. So as soon as the transistor enters saturation mode, VL will be at its maximum negative value. So that happens when VCE becomes equal to VCE stat. So when the collector emitter voltage drops down to VCE stat, the device enters the saturation mode. And under this condition, VL reaches its maximum negative peak. And so we denote it by VL maximum, we denote it by VL maximum negative. So solving this equation, since VCE is equal to VC minus VE and VC is DC voltage plus AC voltage, VE is also DC component plus AC component, we get, so we replace V small c is actually equal to the load voltage. So under this condition, we represent load voltage as VL maximum negative. So VL maximum negative minus small signal VE is equal to negative of VCE minus VCE stat. So VCE is VC, this VC minus VCVE. So we take that to the other side, take negative out common, so this is what we get. So we can find VL maximum negative once we know this small signal component of the emitter current. So the small signal component of the emitter current can be obtained by analyzing the small signal AC equivalent circuit of the common emitter amplifier. We've already analyzed the circuit before, but we found the output current and the output voltages and the output resistance and input resistance, not the emitter voltage. So emitter voltage can be found by finding the small signal emitter current and then multiplying it with RE. So VE is IE times RE, and IE is the sum of three currents. It is equal to IB plus beta IB plus the current through R naught, which we denote by IR naught. We've already found IR naught when we analyzed the common emitter amplifier, and putting that expression in here and solving, we get this result, in which we have written IB as VI over RIB, because by definition RIB is the voltage at the base with respect to ground divided by the base current. So RIB by definition is VI over IB. So in turn IB is VI over RIB, where RIB is the resistance seen looking into the base terminal. So it is this resistance, the resistance seen looking into the base terminal. In other words, it is the resistance seen looking into the board made up of base terminal and the ground node. And like I said, we've already computed IR naught in one of the previous lectures. It is given by this expression. We have expressed VE in terms of VI. We can also express VL in terms of VI. VL is the output voltage now. And from the small signal analysis of common emitter amplifier, we've already computed the output loaded voltage. And this is what it is given by. So taking the ratio of VE to VL cancels this common factor of VI over RIV, and we are left with VE expressed in terms of VL through this relation. This common denominator is also cancelled out. So since we're dividing VE with VL, so the numerator so we are dividing VE with VL. So this numerator, it appears here as the numerator, and this numerator appears as the denominator. This factor appears in the denominator, and this factor appears in the numerator. So this is what we get as the emitter, small signal emitter voltage in terms of the load voltage. So putting this VE back into the equation we had just derived, and since under this condition VL is equal to VL maximum negative, so replacing this with VL maximum negative and putting the resulting expression back into the equation, we get this result. So this is the expression we had just derived for VE, and this is the right hand side. So we take VL maximum out common, so VL maximum negative out common, so we're left with 1 plus this term, and that term is divided on the other side. So this is the exact expression for the maximum negative swing of the output voltage of common emitter amplifier without bypass capacitor. This can be simplified by making use of reasonable approximations, assumptions, such as we can assume that small R0 is much greater than this parallel combination of RC and RL and RE as well. So if we use this approximation, then beta R0 in the denominator becomes almost beta R0. Beta R0 minus RE in the denominator can be approximated with beta R0, and in the numerator beta plus 1 R0 plus this parallel combination, it can be approximated with beta plus 1 R0. And if we assume that alpha is almost 1, then beta plus 1 gets cancelled with beta. R0 gets cancelled with R0, and we are left with this factor. So this is the approximate expression for computing the maximum negative swing of common emitter amplifier without bypass capacitance, which can further be approximated by assuming that this factor is really small, because the inverse of this factor from the small signal analysis of common emitter amplifier, we notice that the inverse of this factor is equal to the gain of the amplifier. It is equal to VL over VI, which is the gain of the amplifier without taking into account the effects of loading on the input side. So this is VL over VI. So if the overall gain of the amplifier is large, then this factor is bound to be large, because the factor that takes into account the loading on the input side is less than 1. So if the overall gain is large, then this factor is even larger, which means that the inverse of this factor, which is this factor, is very small compared to 1. So when the gain of the amplifier is large, we can ignore this factor, and the maximum negative swing of the common emitter amplifier without bypass capacitor is then approximated by this expression. So this is the exact expression, and this is the approximate expression after making use of these assumptions and assuming that this gain is pretty large. So once we know these expressions for a given circuit, we can find the maximum negative and maximum positive swings of the amplifier, and then we take the magnitude of each, and we multiply with 2 the minimum of these two values of the magnitude of VL maximum negative and VL maximum positive. to get the maximum symmetric swing of common emitter amplifier without bypass capacitor. We can find the maximum symmetric swing for common emitter amplifier with bypass capacitor very easily from the results that we have already derived. So this is the same circuit. The only difference is that emitter is at AC ground now. So the output is again taken from the collector, and as VL increases in the positive direction, AC component of DC increases in the positive direction, which decreases this drop across RC, which decreases the current through RC. So VL is increasing in the positive direction, load current is increasing, current through RC is decreasing. So again, as VL increases in the positive direction, collector current decreases. So the maximum positive peak is observed when collector current becomes zero, when the device enters cutoff mode. So like I said, output voltage is the AC component of collector voltage, and it reaches its maximum positive peak value when the transistor enters the cutoff mode. So under this condition, we again replace VL with VL maximum positive. We solve as before, and we get the same expression. Similarly, for the swing of the output voltage in the negative direction, as VL swings in the negative direction, the load current increases and flows in the upward direction into the collector. So as VL increases in the negative direction, load current flows in the upward direction into the collector with increasing magnitude. So since VL is increasing in the negative direction, the AC component of the collector voltage is increasing in the negative direction, which decreases the total collector voltage. So when total collector voltage DC decreases, the drop across RC, it increases, which increases the collector current. So VC is decreasing. VE, so the small signal component of the emitter voltage is zero because of this capacitor. So if we look at the AC equivalent circuit, then this node is at AC ground. So small signal VE is zero, which means that the total emitter voltage is actually equal to the DC voltage. So emitter voltage is fixed. VC is decreasing, hence VCE decreases. And so as VL swings in the negative direction, VCE decreases and drives the transistor towards saturation. So the maximum negative swing of the output voltage is observed when the device enters saturation. And under this condition, we replace VL with VL maximum negative. So small VC is equal to VL, and we denote it with VL maximum negative. And the small signal VE is now zero due to the bypass capacitor, which directly gives us the maximum negative swing of the common emitter amplifier with bypass capacitor equal to this expression. So previously we obtained this expression as an approximation. Here this is an equality. This is the exact expression. And so please notice that we can directly get this result in 16 and this result in 14 by simply replacing RE with 0 in these expressions. So we obtained VL maximum positive like this. For the common emitter amplifier, since there is no RE, so this remains the same. And in this expression for VL maximum negative that we obtained for common emitter configuration without bypass capacitor, if I replace RE with 0, this term becomes 0. And this factor becomes 1. So this becomes an equality as we obtained here. So you can directly obtain the results for common emitter amplifier with bypass capacitor from the results we obtained for common emitter amplifier without bypass capacitor by simply putting RE to 0 in those expressions. Next, we move on to the common base amplifier. So this is the overall circuit for common base amplifier, in which we have CB as a capacitor which brings the base node to AC ground. So again, VL is the AC voltage, VC is the total voltage, IC is this total current, and VE is this total emitter voltage. So we observe that the maximum positive swing of the output voltage is again given by the same expression. Why? Because again you can do the same analysis. As VL swings in the positive direction, the AC component of collector voltage, which is equal to VL, it also swings in the positive direction. So this increases the total voltage VC, which in turn decreases the drop across RC, which in turn decreases the current through RC. So current through RC is decreasing, current through RL is increasing because VL is increasing in the positive direction. This decreases the total current IC because IC is equal to this current minus this current. So IC decreases. So as VL swings in the positive direction, transistor is moved or driven towards the cutoff mode. And the maximum positive peak is observed when transistor enters the cutoff mode. In other words, when IC is 0. So again, going through the same set of equations, replacing VL under this condition with VL maximum positive, we obtain the same result as before. Maximum negative swing is obtained when the transistor enters saturation mode. So as VL swings in the negative direction, the AC component of the collector voltage swings in the negative direction, which decreases the total voltage at the collector. So as VC decreases, the drop across RC will increase, which will increase the current through RC. So the current through RC is increasing. The current through RL, which now flows in the upward direction into the collector, it also increases because as VL increases in the negative direction, the current flows upwards into the collector with increasing magnitude. So the current through the load flows into the collector with increasing magnitude. The current through RC is increasing. This increases the current entering the collector terminal. So collector current increases, which in turn increases the emitter current because IC is equal to alpha IE. So emitter current increases, and since emitter current increases, the drop, the voltage drop across RE, which is given by the voltage at the emitter, it increases. So voltage at the emitter will increase because of the increase in the emitter current. So VE increases, VC decreases, VCE will decrease. So as VCE decreases, the transistor is driven towards saturation. So the maximum negative peak value of the output voltage is observed when the transistor enters saturation mode. That is when VCE becomes equal to VCE sat. VCE is VC minus VE. VC is DC VC, the DC component of VC plus the small signal AC component of the collector voltage. VE has DC component, AC component. So the small signal AC component of the collector voltage is equal to VL, which under this condition is denoted by VL maximum negative. And small signal AC component of the emitter current, because of this negative sign, becomes negative. VC minus VE, the DC quantities, they make VCE, which is taken to the other side. So we get minus of VCE minus VCE sat. And this is the expression for VL max negative, which is obtained when the device enters saturation mode. So this holds when the device enters saturation mode. However, in this case, we note that small VE, which is the small signal AC component of the emitter voltage, it is given by a fraction of V sig, where Ri is the input resistance of the common base amplifier seen looking into the emitter. So if we go back to the circuit, V sig is divided between R sig. So first of all, we've already seen the AC equivalent circuit of common base amplifier in which we short circuit Cin. So there, from the analysis of the circuit, we know that V sig divides itself between R sig and the resistance seen looking into the input of the amplifier, which is the resistance seen looking into the emitter terminal. So voltage drop across the emitter is equal to, is given by the fraction of V sig. So V sig divides itself between R sig and Ri, where Ri is the resistance seen looking into the emitter. So the voltage at the emitter is a fraction of V sig, which is given by this voltage division rule. So Ri is the resistance seen looking into the emitter. So resistance seen looking into the emitter over this factor times V sig gives us the voltage at the emitter. So this is the voltage division of V sig into R sig and R into the voltage across R sig and the voltage across Ri, and this is the voltage across Ri, which is equal to, since Ri is the resistance seen looking into the emitter, so this is equal to the emitter voltage. From the analysis of common base amplifier, we've already seen that Ri is given by this expression. This is the exact expression which can be simplified using this very reasonable assumption into this expression, which can further be simplified because small re is typically much smaller than capital Re. So typically the input resistance of common base amplifier is represented by the small signal emitter resistance, small re. So R sig is also of the order of small re, because small re is of the order of tens of ohms, and R sig typically for signal generators is 50 ohms. So they are almost of the same order. So this fraction is almost 0.5. So if I replace Ri with small re and take VE to the other side, then this is the expression I obtained for the maximum negative peak of the output voltage, which can further be simplified by ignoring this term, because like I said, R sig is almost of the order of Re, small re. Hence, this fraction is of almost 0.5, and V sig is already very small, because V sig is so small that it satisfies the small signal approximation, and this factor is smaller than 1, almost 0.5. So VE is even smaller than V sig. So V sig is already small, VE is even smaller, so this term can be ignored. So once we ignore this term, then we obtain this expression, approximate expression for the maximum negative swing of the common base amplifier, which can be observed to be the same expression as we obtained previously for the common emitter amplifier. So next we analyze common collector amplifier for the maximum positive and negative swing of the output voltage. In this case, however, the output voltage is taken from the emitter terminal. Collector terminal is directly connected to VCC, hence it is at AC ground. IE represents the total emitter current, which is the sum of DC current plus the AC current, and VE is the total emitter voltage, and VL again, because of C out, is purely AC. So in this case, VL is equal to the AC component of VE. So the total load voltage, because of the output coupling capacitor, is equal to the small signal component of the emitter voltage, and hence we denote it with small v, small l. So it is purely AC. So we, like I said, this is the total emitter voltage, and so we observe that as the output voltage swings in the positive direction, so given this emitter voltage, as the output voltage swings in the positive direction, so VL increases in the positive direction, the small signal AC component of the emitter voltage, it swings in the positive direction, because VL is equal to small VE. And since total VE is equal to DC plus the small signal component, so the total emitter voltage increases. So VE increases, VC is fixed, is equal to VCC. So as VE increases and VC is fixed, VCE will decrease. Hence, as the output voltage swings in the positive direction, the transistor is driven towards saturation, because this is the expression for VCE. So VC is fixed and VE is increasing. So during the positive half cycle, the transistor is driven towards saturation, and therefore we observe the maximum positive swing of the output voltage when the device enters saturation. That is under this condition. When VCE drops down to VCE sat, then at that point the output voltage reaches its maximum positive peak value, and under this condition we denotes the output voltage by VL maximum positive. So this is VL under this condition. So VCE is VC minus this VE. So capital VE plus small VE is the total emitter voltage. So VC minus VE is VCE, and like I said, small signal AC component of the emitter voltage is equal to the load voltage, which under this condition is denoted by VL max positive. So VL max positive is given by this expression. So this is the same expression as we have obtained for the other configurations, except that we don't have any negative sign now. Furthermore, as the output voltage swings in the negative direction, voltage at the emitter decreases, which decreases the current through RE. So we look at the circuit again. As VL swings in the negative direction, small VE swings in the negative direction, which decreases VE, because small VE becomes negative and increases in the negative direction, which when added to the DC voltage, DC component of the emitter voltage, decreases the overall VE. So VE decreases, which decreases the current through RE. So the current through RE, which we will represent as I subscript RE, decreases because VE decreases. Moreover, we see that as VL swings in the negative direction, as VL increases in the negative direction, the current through RL, which now flows upwards into the emitter because VL is negative. So the current through RL flows upwards into the emitter with increasing magnitude because VL is increasing in the negative direction. So this current flowing from upwards through RL into the emitter, it increases in magnitude. So this current increases. The current through RE, it decreases. And as a result, the total emitter current, it will decrease because the total emitter current plus the current through RL equals the current through RI, which means that the total emitter current is equal to the current through RE minus the current through RL. So if I show the equation, so the current through, so the total emitter current plus the current through RL, which now increases, which now flows upwards into the emitter terminal. So the emitter current plus the current through RL is equal to the current through RE. So the emitter current is current through RE minus current through RL. Current through RE is decreasing, and current through RL, like I said, is increasing. So when this is decreasing, this is increasing, IE will decrease. So the maximum negative peak of the output voltage will be observed when IE becomes 0, because as IE is increasing, as IE is decreasing, IC is decreasing because IC is alpha IE, and so the transistor is moving towards cutoff mode. So as VL swings in the negative direction, IE decreases, IC decreases, and the transistor moves towards cutoff mode. And the maximum negative peak value of the output voltage will be observed when IE becomes 0. So when IE becomes 0, the current through RE becomes equal to, so from this equation, when IE becomes 0, the current through RE becomes equal to the current flowing through the load in the upward direction into the emitter terminal. So the current through the load flowing up RL, in the upwards direction through RL into the emitter terminal is IRL. So that current equals the current flowing through RE. The current flowing through RE is the voltage across RE, which is the voltage at the emitter, divided by RE. And the current through RL is the voltage at the load divided by RL. But since, so let me go back to the circuit. So VL over RL will give me current flowing downwards. But since I'm considering the current flowing upwards, that will be minus VL over RL. That is why I've represented the current through RL, because the current through RL is flowing upwards. So I denote it with minus VL over RL. And under this condition, VL is denoted by VL maximum negative, because under this condition, we observe the maximum negative peak of the output voltage. So the current through RL is minus VL over RL, and VL is replaced with this, is denoted with this VL maximum negative. So small v subscript capital E is the total emitter voltage, which is equal to DC component plus AC component. I take this to the other side. To the left-hand side, it becomes positive. AC component of the emitter voltage is equal to the load voltage, which again is denoted by VL maximum negative under this condition. So I take VL maximum negative out common. I take this term to the other side. So VE is the voltage across the emitter voltage. VE is actually the voltage across RE because the other end of resistance is grounded. So VE over RE is the DC current IE. And so I take VL maximum negative out common. I take this factor to the other side. So realizing that the inverse of this factor is actually the parallel combination of RE and RL, this is what I get for as an expression for the maximum negative swing of the common collector amplifier. So as unlike before, where we observed the maximum positive swing of the other configurations to be given by IC, RC in parallel with RL, this, because the output is taken from the emitter side, is given by IE and RE in parallel with RL. And obviously it is negative because it is the maximum negative swing of the output voltage. So it has to be negative because this is the AC component. So it is the maximum negative peak value of the output voltage for the common collector amplifier. So knowing these expressions for the maximum positive and maximum negative peaks of different configurations, we can find their magnitude, and whichever of the two is smaller, we multiply it with 2 to get the maximum symmetric swing of the amplifier configuration under consideration. So with this, we reach the end of this lecture. I hope you were able to understand all of these expressions. Again, I would recommend that you go through the analysis yourself and derive and reproduce all of these results yourself in order to get an even better understanding of what is going on here. So thank you very much for your time, and I will see you in the next class. Take care.